Guys, in this video, we're going to implement the derivative of polynomials. And polynomials are going to be just an array of the coefficients of the polynomial. The derivative, of course, in analysis and calculus is some implicit definition requiring a limit over an infinite sequence of some, arithmetic operation under some metric on the real numbers, which themselves require a set theoretical framework to set up, or at least some second order logic axiomatics. We can avoid that if we just restrict our space of functions not to all the functions we can take a derivative of, but to, for example, the polynomials, which really just form a vector space of some countable dimension. And for example, if you think of formal series, infinite power series, then the derivative is just some matrix with natural number coefficients. Actually, it's super sparse. If either this is trivial to you or it sounds very fuzzy, I will get to that eventually, not in this video. In this video, we're just going to do a straightforward implementation, a few one-liners. And if you might think that this is a little often unrelated, then you're wrong. I do this mostly because, in the video a month ago, I was already implementing the gradient descent algorithm in a particular fashion for this deep neural network that I implemented from scratch in Python. And in the last video, I'm already gearing towards a re-implementation of the gradient descent algorithm, the simple example that you find on Wikipedia as well. And I wanted to, break all the aspects of it down, and here we already talked about floating point numbers, and to circumvent that, in the last video I implemented this algorithm that takes some floating point, a rational number, and gives you better and better rational approximations. And I was doing that in this machine framework. I had this wrapper for a while loop. We talked a little bit about Turing completeness and how the while loop enables you to have the full scope of computable operations. I already talked about this like half a year ago when I implemented the hash algorithm SHA and pointed out how this does not require this Turing complete framework at all, because they're not just for loops of fixed size, and if you compute the hash function, then you know in advance already exactly how many like primitive operations you're going to do. And it was not so, for example, here in the approach to a good rational, we had a halting condition, like halting condition you find, for example, also in finite state machines or Turing machines. And in this video, however, we're going to talk about the derivative, right? And this is actually also the case that we know in advance exactly how many operations we're going to do. So here we also just need a for loop. And what I'm going to do is I'm also going to wrap this for loop into this machine framework that I had in the previous two videos. I initially came up with this virtual machine, quotes and quotes, this while loop wrapper in the video on computably enumerable sets. But again, in this video, we're just going to implement polynomials. We have a linear operation at the derivative, and the algebra that we just need is that we need to know that simple rule that if you have a monomial, you take the derivative of that, then the exponent comes down, is multiplied by whatever coefficient might be there in the polynomial, and the new exponent is just reduced by 1. So what's going to happen is if we represent the polynomial as a list of coefficients, then from this exponent that comes down, we have a multiplication of coefficient and this exponent. And then because of this -1, the whole coefficient list will be shifted by 1, right? So the constant term in the polynomial is going to be killed off, and the first one becomes the 0th one, the second one becomes the first one, and so on and so forth. So there's a multiplication and the shift, and this is the whole algorithm that we need. And we're going to implement it in a way that we do a for loop, just for sake of demonstration, implemented via this while loop, and we're going to take the nth derivative. In this case, we're going to look at the polynomial of order 4, and we're going to take the 4th derivative. And so in the polynomial of order 3, meaning 4 coefficients, we take the fourth derivative, so we'll end up with just a 0 polynomial in the end. Okay, so far so good. This was a lot of ranting, but the rest of the video is just coding. Subscribe to the channel, of course, and I don't know, share it to people who want to see this implementation. And this is actually an implementation that also happens in practice, when you have to do some, I don't know, approximation to some things and use polynomials, and the whole thing translates also to, as I said, the formal power series. If you have a analytic function like the exponential function, that's really also just an infinite series of monomials, and so here's the computational implementation of all of this. Okay, so let's go to the coding part. I have here already the virtual machine that I had in the last 2 videos. The only thing that I added, as I just said, and I will just discuss here because I don't want to dwell on this too much. You know, this virtual machine is really just this runner that is computing a while loop and searching for a halting condition, and at each step, as long as it goes, as long as the halting condition doesn't break the loop, the update step is applied. The update step in this video will be taking the derivative. And I extended this virtual machine implementation that I already had in the last 2 videos. In this case, just by adding a maximum number of updates that we want to do. This makes for this while loop, for this for loop basically, in the while loop. So we're going to set this, I don't know, if you set it to 7, then only 7 steps are going to be executed, because at each step the thing remembers that there was an update going on, and next to this custom halting condition, there's also this for loop like halting condition, where it will exactly break once you have this number of steps taken. If you don't set it, if it's just 0, then this will actually never be true, so it will never hold because of that. So this is really a strict generalization of this while loop runner that we had before. Okay, so we're going to implement a printing function that takes this array of coefficients and prints it as a polynomial, even with the name. The name is going to be, you know, in this case p of x. We are going to implement an evaluation function where you pass a value and it evaluates the polynomial given by the coefficient list, and then the derivative. And all of these are basically one-liners. Then the upstep step is the wrapper for the derivative. And here's what we're going to compute. So our example polynomial is this one. So this is the polynomial 2 plus 0 times x plus minus 9 times x to the power of 2 plus 3 times x to the power of 3, right? We're going to print this first, then we're going to evaluate this at some numbers, let's say 1 or 3 or any number really. And then we're going to take the derivative 4 times. So I mean, I could also write here 4, or we can also write here 3, doesn't really matter. And that's pretty much it. So let's just do it. Okay. So printing it will come in 2 parts. We're going to write p of x equals something something. The x is just going to be the name of the variable. So we see this already. We're going to use it like that. So p is the name of the polynomial. X is this variable. The capital X in abstract algebra is the default variable name for that. So we are going to have name of string. So the name is this p. So this is really just p of x is what we want to write. So p of x. So we have this argument brackets. And so this is name and x. So far so good. Then we have the term string, which is going to be a sum of terms. So there's going to be a sum plus a bunch of pluses, and here we have to pass the array or iteration of these terms. What do they look like? Well, I'm going to wrap each term into a separate bracket simply because of the negative signs, right? So that is the easy solution to not having to flip the pluses around. I will just write plus minus and put this in brackets. So this is the coefficient times the value x to the power of the exponent. And the exponent here, this is, as I said, 2, and the constant 2 is really 2 times x to the power of 0, right? And then 0 times x to the power of 1 minus 9 times x to the power of 2. So this 0, 1, 2, 3, 0, 1, 2, 3 is really just the index also of this array. So we can get these numbers. So we do format coefficient, let's call it Cn, and then Xn, and we can access these coefficients by running over this Cn. Cs is going to be the coefficients, right? The coefficient list. So we can access them by saying n for n Cn in, and then enumerate these CSs, and that's it. Let me then just do p of x equals a format name string term string. Okay, let's test. Okay, here before I started the video, I already tested it previously. That would just print nothing, and now if I run this again, it tells me what the polynomial is. So this is the pretty print that we just implemented, right? It runs through the coefficient list and adds this x and the exponents here. So let's go to the evaluation. At the moment it still says none here. How to evaluate it? Well, it's really just the same spiel. We're also going to do this same loop here, but in this case we have to put in not just the variable name x, but the actual value x. But it's really the same thing, right? So this is the coefficient times this value x to the power of n, and so that these are the values, and we're going to sum them up like so. That should be pretty much it. Let's test it on 1. So on 1 we can see the 2 minus 9 is minus 7 plus 3 is minus 4. So that checks out. If you do, I don't know, 3. Right, so we can test this. If we plug in 3 here and add this up, we evaluate it. We can also, of course, take anything here. Let's take this 3.3 into 5. Still checks out. Right? We can take a big number as well. That's what I tested before. Right. Okay. The last algorithm, basically, if you want to call it that, is also just a one-liner. It's going to be taking the derivative. And so we have basically two cases. In if the, you can imagine this polynomial as some coefficients, and at one point, like the power x to the power of 4 is not there anymore. You can imagine just trailing zeros. All coefficients are zeros. So we just take the array as long as we need it. In the case that the array would be just a number, for example, number 2 or number 7, the constant function 7, then the derivative would, of course, just be 0, right? The derivative of the constant is 0. So we're going to make this case distinction. So we're going to look at the length of the coefficient list. If it's 0, then we're going to return still a polynomial, but it's the 0 polynomial. And otherwise, we are going to do this derivative where we take down the exponent, multiply it with the coefficient, and that's basically it. The only thing that we have to do is we have to shift the whole thing because the first element will, the constant term will become 0. We throw it away, and the linear term, something times x, becomes the first one. So we're going to actually skip the first coefficient. So we're going to do an implementation as follows. We say Cn times n. The n is what comes down. The coefficient is already there. But we only do that if n is bigger than 0. So we skip the first element. This becomes just 0. The constant term becomes 0. And so this is how the shifting happens, by leaving out the first element. So now finally the update step for our machine is just really a wrapper for that. And we are going to introduce the same num updates counter to give it a name. Like the second derivative, for example, will be p prime prime. You usually use a prime to say this is the second derivative. So I want to keep track actually of how many derivatives I already took, and that's why I pass in the state not just the coefficient list but also this loop counter, and this what I'm going to update at each operation. So here the state is passed. I bump how many iterations already happened, and then I create this name. The name is going to be p plus these primes. So this is the p prime, p prime prime, p prime prime prime, and so on and so forth. How many do we need? Well, exactly loop counter many. And here we're going to update the coefficient list by just taking the derivative, right? And finally, I will also pretty print it here. So I will take the pretty print function. I will give it a name x again, and here I have to pass this coefficient list that I access from the state. And I think that's it. Let's test. Let's debug. Yeah, error. Okay, I've forgotten here again the CS. So and it works right out of the box. So okay, so let's actually take 6 derivatives. So what do we see? Well, we start of course with this polynomial. We take one derivative, so the 2 will be gone. The first term here is just 0. Right here, this went from x to the power of 1 to x to the power of 0. Then minus 9 times x to the power of 2. The 2 comes down and multiplied by minus 9. This is exactly what happens here. And so in the second derivative, we have minus 18. And incidentally, 3 times 3 is 9 times 2 is also 18. So in the second derivative here also 18. And so on it goes. And after the third derivative, we're just having the 0, and then it sticks at 0. And there you have it. This is how you implement the derivative on an array. Basically just implementing the algebraic operation and shifting around numbers, keeping the basis vectors, this x to the power of something, basis vectors. In if you picture for example picture the polynomial extended by a bunch of trailing zeros as an infinite but countable basis vector space, and all polynomials are just vectors there, then now you might see that the only thing you really have to do is shifting around like mapping the basis vectors, always each basis vector to the previous one in this enumeration, and then multiplying by whatever power is represented by the basis vector. So this is a huge matrix, very sparse elements. But okay, maybe I come back to that in the future. I'm currently looking at constructive set theories and looking at the ordinal analysis, trying to understand them. And that's why I'm also interested in the implementation of in principle analytic, like calculus like operations, and how they for different function spaces become as algebraic, and to what extent you can generalize that to other function spaces. This is what I'm currently looking at a little bit, and I will also make a video about different notions of derivatives in future. That I will make a kind of, let's say, Wikipedia survey where I, in 20 minutes or so, skim through different notions of derivatives. So look forward to that. Thank you for watching this video, and wish you good night.